Welcome back to our second talk, and our second talk will be on Weyl law in Liouville quantum gravity.
All right, thanks. Welcome back. So I want so this is the plan of my talk. I mean, some of you are familiar with this stuff, but some are not. So there'll be I'll sort of do a crash introduction to LQG and tell you a bit about this object, which is the center of the talk, the Liouville Brownian motion, and then I'll try to tell you some of our results for Liouville Brownian motion. They relate to the Weyl law and to the heat kernel short-term asymptotics, and I'll discuss a couple of problems and conjectures. And yeah, feel free to interrupt me. This is slides, so I hope I will not, but I might be tempted to go faster. So it's good if you interrupt. Right, so motivation starts with a very basic question, which is what does a random surface look like? And so this is what it might look like. So you can imagine having a list of surfaces in the bucket, and you pick one without looking at random, and you ask yourself, what does it look like? And this is the sort of thing it might look like. Very different from the kind of smooth surfaces you might have studied in geometry. I don't know, because I never took a geometry course, so but but I'm pretty sure they're different. And mathematically, this is a theory that started emerging in the 2000s, but the roots of this go much they reach much further than that, and the motivations have to do with Liouville quantum gravity or Liouville conformal field theory, which you could think of as 2D generalization of finite path integrals, and this is something that goes back to, in particular, to work of Polyakov in the 80s. So to tell you a bit about this story, it's good to tell you how we're going to talk about our surface, and that's through isothermal coordinates. So here's a surface you'd like to describe, and here's one that you know very well, the sphere. And then the idea is that you can parameterize one by the other, and when you do that, the conformal and the metric structure of the surface on the left is completely encoded on the right by this function on the sphere. Here, D should be the sphere, but later it will be a domain, which is a non-negative number. And this, the meaning of this number, of course, rho of z, is that if I have a curve of length epsilon here, it really is a curve of size rho of z times epsilon over there. So really, what we like to do is describe this rho, and so for this, there is in physics this DDK ansatz, which I think is fair to say was really explained to the math community in this very important paper of Scott and Bertrand from 2010, I think. And this ansatz says that the conformal factor should take the form of the exponential of some parameter gamma times h, where h is a Gaussian free field. So I think many of you know what a Gaussian free field is, so, but still, if you don't, then this is a random generalized function. You can think of it as a function where the function is Gaussian. So if you evaluate it, if you could evaluate it at various points, you'd find a Gaussian vector and the covariance centered, and the covariance would be given by the Green function. And the Green function blows up on the diagonal, so you cannot really do this rigorously. So instead, you test it against function, and then you get a Gaussian unknown variable whose variance is given by this. Okay, so that's the Gaussian free field. And so remember, what we want is not the Gaussian free field, but the exponential of gamma times the Gaussian free field. And there's sort of three things you might want to talk about. Three related things. Maybe the most natural thing would be the metric on the sphere or on the domain D, which is roughly this. Related to that is a volume measure, So again, you could take a region of area epsilon on the sphere and ask, what does it really represent on the horse? And that's something like rho z baby squared times epsilon. And the third object you might want to construct is a diffusion, which will be the Brownian motion on the surface. The way to think about this is that you have your fly that's walking on the horse as it happens, and you look at what happens in this parameterization. You might ask yourself, what does it do, this diffusion? And I think it's a very satisfactory state today. We can actually give a meaning to all three of these things. They are not equally easy or hard to construct. Maybe the easiest thing to construct is the volume measure. Closely related to this is the diffusion, and an order of magnitude more difficult is to construct the metric. And these constructions, we know how to do them for any Gaussian low-correlated field in every dimension, except for the metric, for which the construction is very much two-dimensional. Okay, so that's that. So here's a possible program that I would like to advertise, given that these objects, so they have a meaning. The question is the following: what do classical theorems of geometry or analysis become in Liouville quantum gravity? So this talk, I would like to address a question that I think is very nice, which is related to a famous question of Markatz in 1966, which, so Markatz asked, can you hear the shape of a drum? Meaning, do the eigenvalues determine the shape of a domain? And you could ask the same thing about Liouville quantum gravity. And that, I'm going to answer just a very, very small amount, small portion of this question by talking about the Weyl law in quantum gravity, in Liouville quantum gravity. So I promised a bit of a crash course. So we start with our centered Gaussian field in RD, which might be the GFF, in which case this K here would be the Green function. But as I said, the important thing is that it's logarithmically correlated. And we sort of, in order to give meaning to things, because it's too rough, we first regularize it at scale epsilon. So we convolve it with some modifier at scale epsilon. And the theorem, which in some form goes back to Kahan, 85, some other goes back to this paper of Scott and Bertrand that I've already alluded to, but in this form, you can find it in my paper as well as in one of Shamov, around about the same time. Which, so this tries to define the volume measure. So you remember we want to exponentiate, we want to view the exponential of the gamma times the Gaussian free field as a density with respect to the Lebesgue measure. And that's roughly what we do, except that we have to normalize it and correctly and take a limit as epsilon tend to 0. And the theorem is that this limit exists in probability. You get a measure called Liouville measure, the Gaussian multiplicative chaos associated to this field H. And furthermore, this measure is non-zero if gamma is between 0 and square root 2D. And intuitively, you can think of this measure as being the uniform measure, but viewed in isothermal coordinates. Okay, so yeah. So this is a visualization of this Liouville measure. So what is plotted here is basically the density, approximate density of this measure. It's singular with respect to the Lebesgue measure, but we can pretend that it's not by doing things before the sending epsilon to 0. And when gamma is small, this should we're looking. The density is e to the gamma times the Gaussian free field. So when gamma is small, you should expect something close to the Lebesgue measure. But as you can see, even here for the small value of gamma, you get already something very spiky and pointy. It doesn't look like a constant one. And as you increase the value of gamma, you get something that gets more desperately pointy. And eventually, above the critical value gamma equals to 2 in the 2 dimension, this measure ceases to exist. I mean, or it does exist, but it's 0. Okay, so some properties. So we know this measure is non-zero if and only if the gamma is not too big, so less than 2 in 2 dimensions. We know that it's singular, but does not have any atoms, so no point carries positive mass. It's universal in the sense that the limit is independent of the choice of regularization, and lots of other things are known, conformal covariance, multifractal spectrum, all these things are well understood about the measure. So let me tell you about Liouville Brownian motion, which is a fairly similar story. So remind you that we want to, normally, if we had a real smooth surface, then there would be no problem in defining Brownian motion. Metric defines Laplacian, and once you have a Laplacian, you have a Brownian motion. But obviously here you have to do something else, and this something else is again to regularize and normalize appropriately. And the natural thing is, if everything was smooth, then this is what you would consider. You would take a Brownian motion on your surface and kind of delay it by the appropriate power of the conformal factor. And here we also have to normalize it appropriately. And another way to write this is that you could start by taking an independent Brownian motion in the plane or on the sphere and do an appropriate time change. And this time change takes kind of the same form as what we had in the previous slides. We kind of measure how much of the Gaussian free field is seen by the Brownian path, and use that to time change the Brownian motion. So the theorem, which appears in 2 papers, they have different publication dates, but they were one day apart on the archive. So one by myself and one by Christophe Garban, Rémi Rode, and Vincent Vargas, is that this limit, as epsilon tends to 0, exists. And this is what we call the Liouville Brownian motion. So, yeah.
Excuse me, I'm confused. Can you use the Brownian motion to measure distances?
No. Yeah, initially this is what we were hoping to do. Yeah, I mean, on normally on the smooth manifold, there's no problem in using the Brownian motion to get the metric out of it. Like the quadratic variation kind of gives you the metric in reality. Another way to put it is that if I there's another way to see this. It's not exactly the same thing, but if I have 2 points x and y, and I condition the Brownian motion to go from x to y in time t very short, then what did the Brownian motion do? A geodesic, more or less. So you'd think the Brownian motion encodes the metric, but at the moment it seems that we don't know.
The problem is the crazy irregularity of the shape. You somehow get lost before you get there.
Conceptually, I don't think it's wrong to say that probably the Brownian motion encodes the metric. We just don't know how to do it. At least I don't know how to do it.
Okay, so we know the Brownian motion should recover the measure. Then you have the metric.
Yes,
it's not explicit.
It's not right. It's true. You're right. It's true. So I have this video that I love to show, which tells you what the Liouville Brownian motion does. And maybe I've shown this video a lot of times, but I never get tired of it. I love it. So maybe before I show you the video, let me show you where let me tell you what we're gonna see. So the green stuff is the Gaussian free field, and there'll be a particle moving on this landscape. That's the position of the Liouville Brownian motion. Yeah, I'll show the video and then we talk. That's the best. All right, so that's it. That's all I've got. Sorry. So what do we see? We see a particle that moves, and I think one of the things that you first notice is that it likes to spend time on top of the mountains. Now, the reason it does so is not that it's attracted to the top of the mountain. It's isotropic. It's a time change of ordinary Brownian motion. What happens, however, is that when it's on top of the mountain, it really slows down because of the time change. And that makes sense because, you know, this when the on top of mountain is when the conformal factor is big. And so somehow what that means is that, you know, this region is representing a huge portion of the surface in reality. So the Brownian motion really does have to spend a lot of time there, okay? Conversely, if it's at the bottom of a valley, it just zooms through because it represents a tiny portion of the surface in reality. Okay, does that make sense? So it's not attracted, it just slows down to there. Is that okay? All right, so I think this is very useful in sort of visualizing what happens. This beautiful simulation was not done by me, but by Henry Jackson, who is a former student of mine, and is now working for Google. So, right. So, right. So you can see this is a time change of ordinary Brownian motion, and that's what it's isotropic. It just slows down when it's on top of the mountain. So some properties, we also know lots of stuff about Liouville Brownian motion. It's a continuous trajectory and does not stay stuck. The reason I say that is that, you know, you might think, you know, in the Gaussian free field, the mountains are so high that it might, you know, like so much the top of a mountain that it just never moves there, out of there. And in some sense, that's what's happening when gamma is greater than the critical value. Just never takes off. Another kind of very nice thing, which was proved in this paper by Garban, Roden, Vargas, is that actually it makes sense to almost surely start the trajectory from all points of R2 or the domain simultaneously. And in particular, you can talk about this as a Markov process. It really has a semi-group, and actually it's a Feller semi-group. And yeah, so you can ask about invariant measures for this process, and it turned out the Liouville measure that's constructed in a few slides before is almost surely invariant, let's say an infinite volume. And we know that this process spends all its time in a set of Euclidean measure, or Lebesgue measure 0. The gamma, the so-called gamma thick points of the Gaussian free field. We can even compute the dimension of time spent in the other thick points of the free field. One of the weird properties that I like is that when gamma becomes greater than square root 2 in 2 dimension, the trajectory has 0 derivative at almost every time. So yeah, so it's you know, the mountain starts to be high enough that the process really likes to be there. And so there is, you know, it's almost doesn't take off, but still, you know, you get a non-trivial continuous trajectory. But at almost every time the derivative will be 0. And yeah, so it's possible to show that the spectral dimension is 2. Almost surely we'll come back to that later in the talk. Yeah.
Second point, when it starts from all points simultaneously, you are considering a process where there's coalescence of these motions?
Yeah, so in some sense. So what I mean by that is that it makes sense, you know, to ask what does the process do if I started from X, where X is arbitrary.
Yeah. But here it says, all points simultaneously.
So it's not that I run multiple Liouville Brownian motions from all points, but it's that for every X, I can start the Liouville Brownian motion from X.
Nice.
And it's not obvious because, you know, a priori, well, there's an uncountable number of points. Okay. Yeah.
Yeah, so to show that the Brownian motion determines the measure, it's enough to show that the Brownian motion is a unique invariant measure?
Yes. Yes. So, yeah, I guess that's true. That's not. I mean, that's not actually how we proved it, but yes, yeah. I mean, this invariance is better. I mean, you know, on a finite volume, it's not literally true that it's invariant because, okay, but in infinite volume, it's true. Okay, so I want to talk about the Weyl law for this object. So for that, I need to tell you about the eigenvalues. One thing which I can tell you is, I mean, initially it might look a little scary to ask what are the eigenvalues of this object. And I mean, I find, you know, the generator is kind of hard to describe, but one thing that is easy to describe is the green function, which is the inverse. And the reason for that is that, you know, this thing is just a time change of ordinary Brownian motion. So if I ask myself, how much time starting from X do I spend near Y? Well, it's the same as how much an ordinary Brownian motion would spend near Y, but multiplied by e to the gamma times the Gaussian free field because of the time change. And, you know, at first this looks like a formal thing to say, but then you look at the right-hand side and you realize, yeah, this is a very nice object. The Liouville measure, there's no problem in letting it integrate the green function because that's just logarithmic. So there's no problem in seeing that the right-hand side is almost surely a finite measure, and that's the green function of your Liouville Brownian motion. So once you have the green function, you can talk about eigenvalues and eigenfunctions. And you know, we're going to say lambda is an eigenvalue of Brownian motion if 1 over lambda is an eigenvalue of the green function. So that's the definition, and these things exist. And okay. Related to eigenvalues and to eigenfunction will be the heat kernel of the process. You also have to work a bit to prove the existence of this object. So this will be the PTXY will be the density of the law of the process at time t with respect to Liouville measure. And you can check that there is a density, and this density, furthermore, is almost surely jointly continuous in t, x, and y, which is far from obvious. So there is a well-defined, uniquely well-defined PTXY. So just like in the usual case, you can expand your heat kernel in a basis of an orthonormal basis of eigenfunction, and it takes the form that is always true. This is true for Markov chains, and it's true here. And yeah, both sides are sort of jointly continuous in t, x, and y. I think this is actually how they prove the continuity using this expansion. Okay, so I'm after the Weyl law for this object, and so let me just remind you what is the Weyl law for you know, the standard Weyl law in Euclidean geometry. And so we're going to count the number of eigenvalues of the minus the Laplacian that are less than lambda in some domain D, meaning I kill my Brownian motion when it leaves D, or I put Dirichlet boundary conditions on the outside of D if you want. And the Weyl law says that the number of eigenvalues divided by lambda to the d over 2 is converged to some constant times the Lebesgue measure of this, so the volume of this domain. And so the question is, what is the analog of this law in Liouville quantum gravity? Maybe at first it's not even clear which d you should use. I mean, maybe I should say that the notion of dimension in Liouville quantum gravity is a bit ambiguous. We could talk of the metric dimension, which is essentially unknown except the square root 8/3, where the dimension is 4. We could talk about the topological dimension, so this would always be 2. So here it's not completely clear which d you should use. And so the theorem, so here let's take dimension 2. So that's not the same d as before. This is, we really, you know, Liouville Brownian motion was defined in arbitrary dimension for a log correlated field, but this is a 2-dimensional result. And the theorem says that we fix gamma between 0 and 2, count the number of random eigenvalues less than lambda. Then the theorem is that this divided by lambda converges in probability to some constant, which is explicit, times the Liouville area of the domain D. So it really is an analog of the Weyl law, where the volume is now the random volume, and the scaling is lambda to the d over 2, so d is equal to 2. Yeah. So it's so that's what it is. This is an expression for the constant, which those of you who are familiar with Scott's notion of quantum cone should recognize as a certain function of the gamma quantum cone. Okay, so that's the result for the Weyl law. Any questions on this? Yeah.
Does this CR value related to LCFT correlation function?
I don't know actually.
It's a finite number.
Yeah, it's a fun. Yes,
It's a finite number.
okay, yeah. Yeah, it could be. I mean, you know, I is x into the minus x, and so it's kind of double exponential. It could be. I don't know. So there is sort of an analogous statement for the heat kernel, and the heat kernel says that the theorem says that for that, if I integrate the heat kernel over some region A, then and I send t to 0, then this quantity looks like the area of A divided by t in probability times this same constant that we had before. I should say that this improves on the result that were obtained by Rode and Vargas on the spectral dimension. To say that the spectral dimension is 2 is to say that PTXX looks like 1 over t in the sense that it's t to the minus 1 plus little of 1. So if you want, this kind of is more precise because you get something with a sharp multiplicative constant here. Now you could ask yourself, is it actually the case that this, pointwise, the heat kernel really behaves like this constant divided by t as t tends to 0? Maybe for almost every x. So, so maybe pros and cons. On the negative side, I would say that the dependence on x is very sensitive. The Gaussian free field is, it's not just that it's discontinuous. It doesn't make sense to say that, but it's very homogeneous and there's really a very rich multifractal geometry. So you could think, well, that doesn't look very likely. But you know, on the other hand, I am restricted myself to kind of typical points here, and the Liouville Brownian paths they spend all their time in these typical points, right? So I don't know. So I'm not sure. Yeah.
A silly question, but since the difference is time change.
Yes.
If one looks at the trajectory,
yes,
just the trajectory of sites visited, say up until first exit time from the set.
Yes.
Is it the same as the regular Brownian motion?
Yes, but what is not true?
The time along it.
So if you take a Brownian motion and you condition to return to x, which is what PTXX is asking to do, once you condition to return to x in some finite time, that's going to look very different from a Brownian motion condition to return to x.
Yeah, time means stuff, yes.
Because time is, yeah. So, yeah. Right. So I can completely answer the question that was on the previous. Okay, that one I can actually answer, but let me tell you what we can do. In some Tauberian sense, when you average over the Gaussian free field, we can prove that there is convergence to a certain non-degenerate random variable. And, so Tauberian theorems are tricky to work with. We don't know a Tauberian theorem for convergence in distribution, but we can prove a Tauberian theorem for convergence in probability, and that's convergence in distribution here is enough to rule out that this converges to a constant. In fact, this cannot converge to almost surely on probability to any random variable. So here, let me emphasize, I'm actually averaging over the randomness of the Gaussian free field. So what this suggests is that, but we cannot prove it because, again, we're missing this Tauberian theorem for convergence in distribution. If anybody knows, I'm interested to hear about it. What this suggests, the previous goal, there shouldn't be a dt here. What this suggests is that t times pt converge to a distribution to a certain non-trivial random variable when you average over the randomness of the Gaussian free field. And if this is only when you average, so this is an annealed convergence, if you like, but if you quench on the randomness of the Gaussian free field and ask yourself what happens to t times pt, I think the only possibility is that there are non-trivial logarithmic terms. I would imagine both up and down, but I can't tell you exactly more than that. Presumably, if you understand enough about this random variable, then maybe you can make some guess. Yeah. So this is the
in your previous slide where you
yeah,
this Tauberian thing.
Yeah,
you're still averaging over the free field.
Yeah, exactly. So
this, I mean, yeah. So I have to take some expectation out of that. I mean,
yeah, exactly. So this is
not enough just to average over the time.
Yes, exactly. So because really there will be non-trivial Pointwise fluctuation. So if you want here, what is happening, this is a really convergence in probability. So what's happening is that yes, at each x there are non-trivial logs, but they cancel each other out. And what you see is this when you integrate over a region. So that's why when you integrate over a region, things are well behaved, and we are very fortunate because otherwise the value would just not be true. Yeah. Thanks. Any more questions on this statement? Yeah, you wanted to ask something?
Could you comment on the value of the integral of the conformal factor when evaluated along an a priori selected Brownian path?
This clock, the value of the plot, this thing.
Yes, for a given, I pick a Brownian.
Yeah.
I pick a Wiener process.
Yeah.
And then along this evaluate the time. What can you say about this variable?
Yeah. So I would say to a first approximate. Let's say this was a small ball. Maybe you stop your estimation when you leave a small ball. I would say to a first approximation, you can think of the clock as being something like the volume, the Liouville volume of that ball.
But this integral would converge, surely.
Yeah, that's exactly the content of this theorem. Yeah, and yeah. So roughly speaking, how much time has elapsed for Liouville Brownian motion by the time you've exited that ball? The value of this clock is roughly speaking the Liouville area of that ball. So, I mean, it's wrong, but approximately not too wrong. That's because Brownian motion tends to fill space more or less. I mean,
yeah, except that I'm asking about the specific realization.
Yeah, exactly. But it's that's why. So it's wrong, but it's okay, not too wrong. Okay, so that's what we have in terms of results. I want to make one conjecture and then finish. And this is the following. So that you can hear the shape of Liouville quantum gravity almost surely. This is that if I give you the eigenvalues of Liouville Brownian motion, then you can measurably recover the Gaussian free field.
Why do you believe that?
I think I don't have good reasons to believe it. I think if I'm so I guess the counter examples that we have in sort of deterministic situations are those where there's a lot of symmetry, and I think the randomness of the Gaussian free field just destroys
examples we understand.
Which one?
Maybe I'm not sure. I think like if your domain is kind of generic, I don't know exactly. I think there are results that tell you that.
So what are the counterexamples? I don't remember it.
Yeah, it's weird stuff where somehow the domain you can.
It's a triangle, right? And you flip it and then it's not unitarily equivalent.
Yeah.
But it's like has the same eigenvalues.
There's some weird symmetries that allow you to have exactly the same spectrum, but domains are not exactly the same. And I think if you insist on your domain being sort of generic, in some suitable sense, I don't remember what, then you cannot have that. It's actually known that. But by the way, I could make an even stronger conjecture, but I didn't dare to write it. But maybe I say it, which is here. I imagine that I know the domain in this conjecture. And then, you want to get the Gaussian free field in that domain almost surely. But maybe you could be more bold and say, maybe I don't give you the domain and you can tell me what the domain is, up to rotation and translation, let's say.
In the quantum surface or something? This can be defined on any domain.
Yeah, but no, it's not. I mean, the spectrum is not invariant in any reasonable sense under a conformal map. So,
I see.
It's not a.
No, it is. I mean, if you do the right coordinate change, where you
Right.
to change and add.
Yes, in that sense, yes, because it will be. Yes, but yeah. So right. It's not that if I change the embedding. Okay. Yes. Of course, yes. If you change the embedding, you also need to change the GFF. So maybe up to conformal coordinate.
Metric measure space is recovered.
So that's right. So maybe up to call. Okay. So for the ball conjecture, I need to say up to.
And the statement about generic things, is this for flat domains or is this for curve? What is this generic?
I can't remember.
I see.
I can't remember. I can't remember. Honestly, I can't remember. Well, it could be something like, if you have the boundary is curved, some lower boundary curvature or something.
You also have conjectures about corrections.
Yeah, that's very interesting. I mean, we've been talking a bit about it with Scott. Yeah, I'd love to be able to do that. Yeah, so. I think if if you have your Liouville Brownian motion in the domain D, let's take some subdomain A and look at the eigenvalues in that. I guess the corrections will have something to do with the boundary length measured in a random way. Because that's kind of well defined. Beyond that, I think is like very interesting. But it's very already quite hard to do the volume part, and I mean, I think there's a lot to explore in this direction. Yeah, that's very much one of the things I'd like to do. Yeah.
Does it make sense to think of local statistics like they do in random matrices to say that something is Poisson-like or Dyson?
Yeah, that's. Yeah, I think I'm not sure. I don't have a good answer to this. I do think it's sort of nice to ask about things like that you might ask in sort of more random matrices or Anderson like story maybe don't has some intuition about this, but you could ask yourself, if I take a very big box, do the eigenfunction become localized or are they delocalized?
But you probably expect them anyway to lie on the support of the measure, which is the.
I'm not sure. No, I don't think so.
No?
No, they have to be sort of nice. Like the heat kernel is a continuous function, right? The eigenfunctions, they have to be nice as well. They're also continuous, actually.
You don't think their support somehow reflects the where the Brownian motion spends most of the time?
They'll be supported everywhere. I mean, yes, they will be big.
Right.
where the Gaussian free field is sort of macroscopically big.
Right.
But it's not like these stick points which supports in some sense the Liouville measure. You won't see them, I think, play a special role in the eigenfunctions. I think.
Any other questions? If there's no question, let's thank Nathanaël.